So it's my pleasure to invite John to give us a talk. It's John Harding. He's from New Mexico State University, and he's going to speak to us on quantum monadic algebras.
Thank you, Joanne, and thank you, everybody. It's great to be here and see so many people I haven't seen in a long time. It's really, really feels good. So this is hopefully the first step in a bit of a larger project. And the real aim that I have is to renew the perspectives of lattices, geometry, and logic in the study of operator algebras. And in particularly in something called subfactors. So a bit of history here is from the 30s to the 70s. There was an amazing group of papers, and starting with von Neumann and Stone, a modern version of the spectral theorem. This was Stone's motivation for his Stone's representation theory. And then Birkhoff and Menger, they had a lattice theoretic perspective on projective geometry. This motivated Birkhoff and von Neumann with their logic of quantum mechanics. And what this was the idea that the projections of a Hilbert space could replace the Boolean algebra of events of a classical system. Mixed in with this is von Neumann's continuous geometries and his representation theorem of complemented modular lattices. Murray and von Neumann, in a series of papers, developed what are now known as von Neumann algebras. Much of the basics theory of it is in here. Frank and Prenowitz, they made an infinite dimensional lattice theoretic version of projective geometry. Kaplansky's complete modular ortholattices are continuous geometries. Gleason showed that the states of a quantum system could be described as in lattice theoretic terms from the projection lattice. Dye showed that the morphisms of von Neumann algebras are determined by their actions on projections. Veradarajan had a geometric quantum mechanics, which basically takes the view of projective geometry. It's a bit of a generalization of projective geometry, and it lives off a fragment of projective geometry. And then various developments of orthomodular lattices related to von Neumann algebras. And so this was a really cohesive, interrelated group of results. And to some extent, it's sort of, this perspective has sort of faded away with many developments. So, I mean, of course, people still know this, but the more modern version of things does not take the same lattice theoretic perspective nearly to this extent. And I'm going to give you a whole bunch of background here that's probably not up the alley of a lot of people at BLAST, but maybe certainly some. So it won't matter if every single detail gets across here. Just the general viewpoint, I think, is going to be enough. We'll start with the bounded operators of the Hilbert space. Okay, so that's like a fancy matrix algebra. And in particular, you have a star operation given by adjoint. You can multiply, add, and so forth. A von Neumann algebra, M, so that'll be a symbol for a von Neumann algebra throughout, is it's a subalgebra of this that's closed in some particular topology. Okay? An element in a von Neumann algebra, so remember it's an operator, is called a projection if it's idempotent and it's self-adjoint. Now, here's the object we're after. The projections of a von Neumann algebra, we order it in this way. P, one projection less than or equal to the other, if they commute and their product is the first one. It turns out that this is not only a partial ordering, this is a lattice, and that this is a complete lattice, and actually it's a complete ortholattice. Complement is not given by star, right? Because star doesn't do anything. Complement is 1 minus. Right? A von Neumann algebra is called a factor if its center, if the center of its projections, so the projections that commute with all others are just 0 and 1. An inclusion of factors is called a subfactor. So you might think, well, why would I care about subfactors? That's a fair enough question, but there's a lot of reasons why. I'm not the best person to explain it, but there's a lot of combinatorics in how this inclusion works. And this was what Jones did, and in his work with knot theory. And there's many other ways to view this combinatorics, planar algebras, and many other things. So there's a vast literature of these things that pertains to many things. Okay? Now, a couple of basic facts that we need is that the projections of a von Neumann algebra form a complete orthomodular lattice. A von Neumann algebra is determined up to Jordan isomorphism by its projections. So a Jordan isomorphism is an isomorphism that doesn't quite preserve the regular product, A times B, but the symmetrized product, AB plus BA. Okay. But this says that the projections largely fill this out, which is very different from a C-star algebra. A C-star algebra does not need to have any projections other than 0 and 1. You don't get anywhere looking at C-star algebras by looking at projections. But you do with von Neumann algebras. This, for the most part, this does a lot. And so a factor has a unique dimension function, which is a certain kind of map from its projection lattice to the extended reals. And factors are characterized into types according to the range of this dimension function. I mean, if the range is 1 to n, then it's a matrix algebra. And if its range is the real unit interval, then it's a continuous geometry. Yeah? And there's other things. Now, C-star algebras are often viewed as non-commutative topological spaces because in the commutative C-star algebras are given by certain topological spaces. This is well-known duality theory. Also, von Neumann algebras are viewed as non-commutative measure spaces because in the commutative setting, a commutative von Neumann algebra is given by a measure algebra. Okay? So this is the start of a long series of things where you view quantum things as non-commutative versions of things that we understand well. Okay? Now, things don't always mesh up perfectly, but it does provide intuition in working with them and how they place together and stuff like that. Now, here's the key observation for us. I'm going to take a subfactor. So this von Neumann algebra is a subalgebra of this one. And they're factors. Then the projection lattice of the smaller guy is a complete subortholattice of the projection of the bigger guy. So if I take a projection in the bigger guy, it'll have its smallest guy in the little one above it, namely the meat of all the things in the smaller one above it. And it will also have a largest guy in the little one beneath it. And I use this suggestive notation for the least above and the largest below. And this is the very familiar thing from logic, classical logic, right? So a monadic algebra goes back to Helmholtz in the 50s, is that a quantifier on a Boolean algebra is a map that has these certain innocuous properties. Preserves finite joins, increasing, a closure operator. And this one is the interesting one. It says that a closed element, the complement of a closed element is closed. Now, you can rewrite these in the Boolean setting. Instead of using these 5, you can use the first one, first 2, and this thing is a shorter thing. We won't do that because it doesn't work this way. When we move out of this setting, this is no good to us anymore. But these are the ones that are more meaningful anyways. We'll keep the longer version. You know. So an ortholattice is a bounded lattice with a unary operation that's complement, switches order, inverts order, and its period too. It's an orthomodular lattice if it additionally satisfies this identity. So every Boolean algebra is an orthomodular lattice, but not conversely. This is much more natural than it looks, but I'm not going to talk about that now. This is just like the modular law. It's a quick way to say something. So monadic ortholattices are just ortholattices with a quantifier satisfying these 4 things or 5 things that we had before. So we just changed the carrier from being a Boolean algebra to being an ortholattice. And a quantum monadic algebra is the same thing, except we make the carrier be an orthomodular lattice. And so abbreviation is quantum monadic algebra. So a few basic examples. If L is a complete ortholattice and C is a complete subalgebra. So by complete subalgebra, I mean that C is complete and that all joins and meets in C are the same as what they are in L. Okay, so that's complete subalgebra. Then if you have that, for anything in L, I can just take the meet of the things in C above it. And this will be in C, and this gives you a quantifier on L, and that's a monadic ortholattice. All complete monadic ortholattices are obtained this way. So complete monadic ortholattices are the same thing really as giving a pair consisting of a complete ortholattice and a complete sublattice of it. If L is a complete orthomodular lattice and B is what we call a block, that means it's a maximal Boolean subalgebra, then it turns out that B is a complete sublattice, and so it gives you one of these quantum monadic things. Now, just to make a little finite example, this is an orthomodular lattice. If you look at it, this is an 8-element Boolean algebra drawn in a funny way. So is this, and they're glued together. All orthomodular lattices are really Boolean algebras glued together in some way. The complexity of the theory comes from how you glue these things together. But in any event, if that's X, then this exists X, the smallest guy and this guy above him. Okay? All right, so let's do some more examples now. So these are von Neumann algebras. Okay? They don't have to be factors, it doesn't matter. But if these are von Neumann algebras and N is a von Neumann subalgebra of M, so it's a subalgebra in the algebraic sense, it's a von Neumann subalgebra of here, then it turns out that the projections of N is a complete sublattice of this complete orthomodular lattice projections of M. And so this yields a quantum monadic algebra. So a von Neumann algebra M then is specified up to Jordan isomorphism by this quantum monadic algebra. Right? It's M itself is a subalgebra of the projections of some Hilbert space, right? So von Neumann algebras are specified by these quantum monadic algebras. And the same with a subfactor. A subfactor will also give you a quantum monadic algebra, and this quantum monadic algebra specifies a subfactor up to Jordan isomorphisms.
Sorry. So this P of H, Should be like P of B.
Yes, it should be P of, it's just too ugly. But exactly, yes, it's an abusive notation.
Yeah.
So the slogan then is that subfactors are non-commutative monadic algebras. It's just a slogan, but sort of like von Neumann algebras are non-commutative measure theory. Okay, so if we start to go a little deeper in the theory of subfactors, and as I said at the start, this is just the start of what I want. This is just the first, hopefully the start of my project. There's certainly a lot more to do, but here's one interesting step. A subfactor has a conditional expectation, at least often it does, associated with it. And this generalizes conditional expectation from measure theory. And I'm not going to tell you this is some certain kind of map with certain properties. I'm not going to go off track to give you the details of what it is, but let me just give you the shape of what's going on. If you, a prominent definition in subfactor theory is that if you have two subfactors of the same von Neumann algebra, they form a commuting square, written this way, if the conditional, this guy gives you a conditional expectation and so does this one. They're both, they both map into M, so it makes sense to talk about them commuting. And so this is called a commuting square of subfactors, and they play an important role in things. And they roughly give a non-commutative version of independent sigma algebras. Now, it turns out that these conditional expectations commute if and only if the corresponding quantifiers for these subfactors. So now we move into the realm where we have more than one quantifier and they commute. And so we'll recognize this as the idea of cylindric algebras. So, and this is sort of, goes back to Tarski and Hengen, Tarski and Monk, the idea of cylindric algebras. In an I-dimensional cylindric algebra is a Boolean algebra with a family of quantifiers in the sense that we used before, and also some constants. Now, the conditions are that, well, we have quantifiers, the quantifiers commute, and then some conditions relating the quantifiers and these constants. Well, so here just a little condition about the constants, not much there. Then we have this little condition, and this one plays really interesting role, C5. So these quantifiers are often called cylindrifications, and these are called diagonals. If you remove the diagonals, you get what's called a diagonal-free cylindric algebra, surprisingly. And this condition here, it's a bit of an unusual looking condition. What it does is there are different ways to formulate it. This has the consequence of showing that this thing here winds up being a substitution endomorphism. Okay, fair enough. The motivating example of cylindric algebras comes this way. Suppose you take x times x. My Boolean algebra is the power set of x squared, and for any set A, subset of x times x, I make it cylindrification like that. This cylindrification. The other cylindrification would go this way. Of course, the diagonal would be that. This is a two-dimensional cylindric set algebra. And so the corresponding quantum thing is cylindric ortholattices are the corresponding structures of Boolean algebras replaced by ortholattices and quantum cylindric algebras with orthomodular lattices. Now, these quantum cylindric set algebras, so they have some superficial ties so far to these commuting squares of subfactors. I need to look into this farther, but let me go into one that's worked out in a little bit more detail. Nick Weaver has something that has a version of quantum logic, And what he does is he takes, if you take a family of Hilbert spaces, I'll do things for finitely many, but you can do it for infinitely many. Then for each I can define a subalgebra of the bounded operators on the tensor product in this way. This does give you a von Neumann subalgebra. And so since it gives you a von Neumann subalgebra, it gives you quantifier. And if all the HIs are the same, then I can define diagonals to be the projection. So it's a projection, that's an element of my projection lattice. So projection onto the subspace of the tensor power that's symmetric, like the symmetric tensor product, but just restricted to those coordinates. And this generalizes to infinite tensor products as well. And so this always gives you a diagonal free quantum cylindric set algebra. If you make these the same, you get conditions C1 through C4, but you do not get condition C5. And there's a good reason. A projection lattice is not going to have a lot of endomorphisms. No matter what you do, it's not going to change that. So there's going to be some kind of issue if you try to make endomorphisms of a projection lattice. And so Weaver's quantum logic will have issues with substitution. And this is sort of an unavoidable thing, but there are other issues with quantum logic. I mean, we have to expect that not everything works the same. I mean, you don't have distributivity in quantum logic. This is something we have to live with. Things are different. And so anyways, I won't dwell on it too much. So some of the issues with C5 are addressed by modifying the axiom C5 to use the Sasaki projections in here instead of this, if you know what those are. Okay, I've got a few minutes left. Let me finish up with sort of something that's monadic orthoframes. So here, with monadic algebras, they have dual structures, basically cryptoframes. And let's talk about that for a couple of minutes. Now, what we want to do here is add a feature. So a relational structure, I'm going to have a set with two binary relations. It's going to be called a monadic orthoframe if this one is what's called an orthogonality relation, meaning it's symmetric or reflexive. And then this one is going to be the one that corresponds to the extra operation of a monadic algebra. It's going to be reflexive and transitive, but not symmetric, and it will satisfy this that links it to the orthogonality relation. If you make this thing not equals, then a monadic orthoframe is basically a set with an equivalence relation, which is the usual thing for monadic algebras. And if I have a monadic orthoframe, the way I go back to get a structure is I take the Galois closed subsets of the polars of this thing, basically. And I define a unary operation on that by exists say to be the Galois closure of R of A. And each one of these things is a monadic ortholattice. Each monadic ortholattice is a subalgebra as such, and each complete monadic ortholattice is isomorphic as such. Basically, instead of working with the canonical extension here, I'm working with a McNeil completion. Okay. And you can do a similar thing for diagonal free cylindric orthoframes. You can have the diagonals if you want. It's not very hard. You just have a bunch of extra operations that can group each other. And you get the same theorems as before. Now, it would be nice to put quantum in these. There are many obstacles to providing similar results for quantum monadic frames. For example, it is not known whether every orthomodular lattice can be embedded into a complete orthomodular lattice. And so that's going to be an issue when you try to get these theorems, okay? And so just to wind up, if this talk is in, it will be in Journal Physics A, it's online now, it's on the archive. But there's a bunch of logical things to pursue with this. And I think they're interesting, but my real motivation is I'd really like to look at more at, there's a lot of operator algebra, of sub-factor things. And I think that I hope that if you look hard, you can find ways that these things make sense in a lattice theoretic, projective geometric way. And maybe my pipe dream is that you can lift them a little bit farther, because the lattice theoretic and projective geometric setting is more general than the von Neumann algebra setting. And so that would be my ultimate hope, but we'll see how far my luck holds out. Okay, so thank you very much.
A few minutes for questions. Anyone?
Hi. Yeah, there's a close connection between cylindric algebras and relation algebras. So my question is whether you thought about extending that into this realm, because I would guess it has something to do with connections between your monadic author lattices and some sort of monadic residuated lattices.
This probably fits exactly in here. There's a lot of really, I haven't done this yet. I think this is a very interesting direction, and there's a bunch of other logical questions to look at. And I would welcome company in looking at these things. I do want to look at the sub-factors too. So I'm feeling torn in two directions to go, but this is that's certainly an interesting thing to look at, Peter. Yes, I haven't done it.
Other questions?
No,
No.
I'm just waving hello to John.
Ah, okay. All right, well, if there are no other questions, let's thank John again.